first, let's write down all the titles under mechanics. Initially we get linear motion, and then we have projectiles under it, projectiles, and then we have Newton's laws, alright, and then we have conservation of momentum, of momentum, and then we get work, energy, power, right? Then we have rotational motion, and then we have circular motion, that in fluid statics. Then finally we have fluid dynamics, right? These are the titles we have under mechanics. Linear motion equations. Under linear motion we have few equations. S equals ut plus half at squared, where S is the displacement, and u initial velocity, and a acceleration, and t is time. V final velocity, u initial velocity, a acceleration, v equals u plus at, and third equation v squared equals u squared plus 2as. Then moving into projectiles. In projectiles, let's say initial velocity is v angle theta. On this direction we get v cos theta. Upwards we get v sin theta. So we have few equations we should remember. The range, once you simplify, we get an equation v squared over g sin 2 theta. Newton's laws. Under Newton's laws we have few equations. The first equation we can use as P equals mv. This is momentum, mass into velocity. Second equation that comes from the Newton's laws, second law, the force applied on an object when it is moving, force is proportional to or is equal to rate of change in momentum, right? So we can write this as even F equals ma. Then we have, under this we have friction equations. So for frictional force, F equals mu r, where r is the reaction force, right? So we have two mu values, stationary mu s, and in motion dynamic mu d, right? Then there's another equation from F equals delta mv over t, F into t delta mv. Here this is, we take it as impulse almost equal to delta mv change in momentum. Conservation of momentum. We can apply conservation of momentum if force applied is 0 or the external unbalanced force is 0. Then we can conclude initial momentum m1 v1 is equal to the final momentum m2 v2. Moving into work, energy, power. Work, W equals force into displacement, and energy, we have two types of energy. We have potential energy and we have kinetic energy. Kinetic energy equation, E equals half mv squared, where m is mass, v is velocity. Potential energy, we have two potential energies. Gravitational potential energy, that equals mgh, and we have strain energy, that is half k x squared. K is the force constant, x is the displacement from the center. Then we have power. Power equals energy divided by time, and units are watts. Moving into rotational motion. To rotate something, we need to apply a torque. Torque equals force into displacement towards the center. Torque. So when applying a force, the torque, the force will be this and distance will be this, F into D, and it will rotate around this point. Tau equals Ft. Then next equation, tau equals I alpha. Here I is the reluctance to rotate or else moment of inertia, where I equals common equation sigma m r squared. Here alpha is the angular acceleration. Where torque is 0, we can conclude angular momentum is conserved. So I1 omega 1 equals I2 omega 2. Then we have kinetic energy, angular kinetic energy. Angular kinetic energy E equals half I omega squared. Moving into circular motion. To move in a circular motion, we need a force towards the center of the circle, right? So this force is called centripetal force. That equals, if the velocity is v, radius is r, m v squared over r. Here we can write it as m r omega squared as well. And acceleration towards the center, v squared over r, and that r omega squared. Then angular motion versus linear motion. The connection is this: S equals r theta, where theta is the angle, radian angle, that divided by t, we can divide this by t. Then S divided by t, you know S divided by t is v, and theta divided by t, we call it omega, angular velocity. Again we can divide it by t, then velocity divided by t, that is acceleration, and omega divided by t, angular acceleration. Hydrostatics. In hydrostatics, first equation we get is upthrust. So here you can see this object is partially immersed in the liquid. So upthrust acted upon it, U equals V rho G, where V is the immersed volume of the object. Here this V, and rho is the density of the liquid, right? And for this object to float, the weight of the object has to be equal to the upthrust V rho G. So this is called floating theorem, right? Moving into Pascal's equation in hydrostat. Pascal's equation, F1 over A1, force divided by area, is equal to this force divided by area A2. So the pressure can be transferred through the liquid in it, right? Hydrodynamics. In hydrodynamics, first equation we call this equation of continuity. A1 V1, here velocity here V1 equals to A1 V1 equals A2 V2. Moving into Bernoulli's equation, pressure plus half rho V squared velocity plus rho GH equals a constant. And there's a derived equation for some questions. It's quite useful to remember the equation. In a question like this, where the water flows out of it from a height h, we can consider velocity. We can derive the equation velocity equals root 2gh by using Bernoulli's equation.